Now in this session we are going to see the Fermi energy in semiconductor and Hall effect in the topic material science. Expression for Fermi level in intrinsic semiconductor. As we have already seen in the previous sessions, the expression for the electron concentration and the expression for the hole concentration. Now we are going to use those two expressions to derive an expression for Fermi level in intrinsic semiconductor. The concentration of electron charge carriers is given by Ne, which is equal to 4 root 2 pi Me star kT by h square whole to the power of 3 by 2 and e to the power of Ef minus Eg by kT, which is equation 1. Similarly, the concentration of hole charge carriers is given by Nh is equal to 4 root 2 pi mh star kT by h square whole to the power of 3 by 2 e to the power of minus Ef by kT. Let this be equation 2. We know that in an intrinsic semiconductor, number of electrons is equal to number of holes. Therefore, from equations 1, 2 and 3, we can get the equation as Me star whole to the power of 3 by 2 e to the power of Ef minus Eg by kT is equal to Mh star whole to the power of 3 by 2 e to the power of Ef by kT. Doing the simplification, you will be getting e to the power of 2 Ef minus Eg by kT is equal to Mh star by Me star whole to the power of 3 by 2. Taking natural log on both the sides, E gets cancelled. So 2 Ef minus Eg by kT is equal to 3 by 2 ln Mh star by Me star. Rearranging the terms, you will be getting Ef is equal to 3 by 4 kT ln of Mh star by Me star plus Eg by 2. Practically, Me star is equal to Mh star. Therefore, ln Mh by Me goes to 1. That ln 1 is nothing but 0. Therefore, the first term in this equation goes to 0. Therefore, Ef is equal to Eg by 2. So, the Fermi level is in the middle of the energy gap in an intrinsic semiconductor because Ef is equal to Eg by 2. This expression says that Fermi level is in the middle of the energy gap for an intrinsic semiconductor. Now we will see the Hall effect. A name of a scientist, Hall, has given this. So the name is been given as Hall effect. When magnetic field is applied perpendicular to the direction of the current in a conductor, the potential difference develops along the direction perpendicular to both the current and the magnetic field. This effect is known as Hall effect. So what exactly is being told here is, when the magnetic field is applied perpendicular to the direction of the current in a conductor, the potential difference is developed along the direction perpendicular to both the current and magnetic field. Now we will see how exactly this effect is being observed and taken. Consider a rectangular slab of an n-type semiconductor carrying a current I along a positive x-axis. That means n-type semiconductor is nothing but the majority charge carriers are electrons and the current I is along the positive x-axis. You can see in the diagram which is bolded, I is along the positive x-axis and B is applied along the negative z-axis. You can see the arrow marks which is nothing but negative z-axis. Now according to Fleming's left hand rule, the Lorentz force on the electrons is along the positive y-axis. Lorentz force, according to the Fleming's left hand rule, the force is exhibited along the positive y-axis. As a result, the density of electrons increases on the upper side of the material and the lower side becomes relatively positive. So, electrons increases to the upper side because the force is experienced towards the positive y-axis. The electrons are moved towards the positive y-axis and electrons are separated from the lower side. So, electrons are being separated. Therefore, what is happening? Lower side becomes relatively positive. The potential developed is VH, called as a Hall voltage. VH is nothing but a Hall voltage, the name of a scientist. Next, we are going to see the expression for electron concentration. At equilibrium, Lorentz force is equal to force due to electrons, that is BeVD is equal to E into EH. B is the magnetic field, VD is the drift velocity, and EH is nothing but the electric field that is developed. EH, Hall. EH is equal to, rearranging EE gets cancelled, EH is equal to BVD. This is equation 1. If L is the distance between upper and lower surfaces of the slab, but EH is equal to VH by L. This equation we are getting E is equal to, we have the equation V is equal to E into D. So rearranging the terms, EH is equal to VH by L, equation 2. So from this, VH is equal to L into EH, that can be written as L into BVD from equation 1. Now current density J is equal to I by A, we know it, and I by A is nothing but J. J is equal to NEVD, which is nothing but I by LD. From the equations, we have got it as VD is equal to I by NELD. Rearranging the terms over here, you will be getting the equation 4. From 3 and 4. Taking the value equations from 3 and 4, VH can be taken as LBI by NELD. That is BI by NED. That is equation 5. Now if you look at these equations, which are numbered 1, 2, 3 and so on, without equation 1 you cannot get equation 3. So it is interdependent, so equations should be numbered and taken properly. So from here, from 3 and 4, VH is nothing but the Hall voltage is nothing but LBI by NELD. That is rearranging again, cancellation BI by NED. Now the charge concentration N is equal to, from equation 5, rearranging the terms, you can get it as BI by ED into VH. Now the expression for the Hall coefficient. The Hall field is directly proportional to the current density J and the magnetic field B. EH is proportional to J into B, that is Hall field, electric field EH is equal to RH into JB, where RH is nothing but the Hall coefficient. From equation 1 and 6, V and J is equal to NEVD. I'll show you the equations here from equations 1 and 6. That is EH is equal to BVD and N is equal to BI by EDVH. Taking those two equations and J is equal to NEVD, we are getting as RH is equal to EH by JB, and substituting the values of EH and JB, it is nothing but VH into D by BI. That is equation 8. That is RH is equal to 1 by NE or RH is equal to VH into D by BI. This is equation 8. Now the expression for the mobility of the charge carriers. Mu is equal to VD by E. We know this equation. In the previous sessions also we have used. So mu is equal to VD by E. Equation 9. The current density J is nothing but J is equal to sigma E. We know that NEVD is equal, J is nothing but NEVD, that is equal to sigma E, and NE, taking the value of VD, substituting there here, NE mu E is equal to sigma E. We have taken from equation 9, that is the above equation, and J is equal to NEVD. And we also know that RH is equal to 1 by NE from equation 8. So substituting all these things, we are getting mu is equal to sigma into RH. So expression for mobility charge carrier is mu is equal to sigma into RH, where RH is the Hall coefficient. Next, what are the uses of Hall effect? Hall effect can be used to determine the type of a semiconductor, whether it is a p-type or an n-type. Hall effect is also used to calculate the carrier concentration and the mobility. To calculate magnetic flux density also, Hall effect can be used. And last but not the least, Hall effect is used to determine the power in the electromagnetic wave. These are some of the uses where the Hall effect can be used effectively. Thank you.